Hello and welcome back to the BioRT-HBV modeling video series on carbonate weathering. This is the second video on setting up the carbonate weathering reaction in BioRT. So if you missed the first video with all the background information, please go and check that out first. So in this video, I'll go over the BioRT input files and how to set up a carbonate weathering reaction. And so the major input files that we'll be discussing include the database or CDBS file, the chemistry or chem file, the initial condition or CINI file, and the precipitation chemistry or precip-chem file. So as we went over in the first video, the calcium carbonate weathering reaction is written in the BioRT database following the reaction pathway on the bottom here, where we have solid calcium carbonate forming calcium ions and carbonate ions. And so this is the reaction that we'll be setting up in BioRT. Right, so the majority of the reaction information is located in the database or CDBS file. And a few key things to remember are that calcium carbonate is written as calcite in the database. The calcium ion is written as Ca++, and the carbonate ion is written as CO3-. And so in all of the input files, just be sure to check that your species names are consistent with how it's written in the database. All right, so in the database, there are two places with important information for reactions, the thermodynamics block and the kinetics block. And so starting with the thermodynamics block, this line is shown for calcite and was taken directly from the database. And so this line contains the reaction equation, stoichiometry, molar volume of the mineral, equilibrium constants, and the molecular weight of the mineral. And so walking through this line from left to right, we have calcite as our mineral. The number starting with 36 is our molar volume of calcite. The number 2 represents the number of products or species on the right side of the reaction. And so the number 1 represents the stoichiometric coefficient for those products. So we have calcium and carbonate both having stoichiometric coefficients of 1. And then the 8 values starting at minus 8.480 are the 8 equilibrium constants or log KEQ values of a reaction given at 8 different temperature points from 0 to 300 degrees. And so we typically just use the second value at 25 degrees Celsius by default. And then lastly, we have the number starting with 100, which is the molecular weight of calcite. And so as we discussed in a previous video, the KEQ value determines the extent of the weathering reaction. So essentially how much calcite can dissolve before the reaction reaches equilibrium. Right, and so now we have the kinetics block, and the entry for calcite is shown here. And each entry starts with the name of the mineral being weathered, which should be consistent with the line in the mineral or the thermodynamics block above. And so the label name here is default, which we'll need to specify in the chem file later on. The type is TST, which corresponds to the TST rate law that's used to quantify the reaction rate. And the rate here corresponds to the K3 kinetic rate constant value in the TST rate law written out on the right-hand side of the slide. The activation corresponds to activation energy, and the dependence line is where you would specify a dependence on a certain chemical species. So for instance, hydrogen ions or hydroxide ions. However, we will not be considering those dependencies in this example. So our rate law equation can be simplified as shown on the right. Right now, because we have carbonate species in our systems, including aqueous carbon dioxide, so we have to consider the gas-aqueous exchange reaction between gaseous and aqueous CO2. And so when aqueous CO2 is saturated in water, it can become CO2 gas and vice versa. And so we represent this reaction as CO2 gas on the left side of the reaction and CO2 aqueous on the right. And so we have this reaction in BioRT set up with a TST rate law. And so we can set it up similarly to how we set up the calcite weathering reaction. And so the entries for the CO2 gas aqueous exchange reaction are shown here. And those entries are located in the same blocks of the database, the thermodynamics block and the kinetics block. All right, so now we'll walk through the different input files that we need to amend in order to set up our reaction in BioRT. And so these files include the chemistry file, the initial condition file, the precipitation chemistry file, and the numerical experiment precipitation chemistry file. Okay, so the top of the chemistry file looks like this and has some important model settings. And I've changed anything here that's commented out in the input file to the color green. That way we can differentiate a little bit easier. But walking through this one by one, the recycle line is set to 2 here, so the model will run through the time series of our simulation twice before running a third final simulation. And so the output file of the results will essentially have 3 series of simulations. Next, we keep the activity line set to 1, so activity will be corrected by the Debye-Huckel equation, where the Debye-Huckel size parameters for different species are listed in the database. Now, for the third line, since we're running a reaction in the simulation, we want the transport only line set to 0 so that we turn on the reactions. Next, the precip chem line is set to 1, so we need to include a time series of precipitation chemistry for our simulation. And if you don't have this data, you can set this line equal to 0, and the model will use the constant precipitation chemistry that's defined in the CINI file. Next, the numerical experiment, or num-exp line, is set to 1, so we need to include separate numerical experiment files for the precipitation chemistry as well as the HBV results file. And so in this example, I'm just going to copy the same contents of the precip chem and results files to the numerical experiment equivalent files. And that way, I'm just going to look at one period of the simulation in the numerical experiment results file instead of going through the 3 recycle periods in the regular results file. And so lastly, the temperature line is set to 25, which is the temperature point for our equilibrium constants in the database. This is where we list out all of our primary and secondary species, as well as the minerals or species that require mass conservation equations. So in this example, those have the TST rate laws. And so in general, the best practice for listing out species is to list aqueous species first and solid species last. And so as mentioned in the previous video, certain species are already listed in the database file under the primary species block, so double check there before choosing your primary species. And so in this example, we have pH, which is used for the hydrogen ion, bicarbonate, and calcium are all listed as primary species. And we also have to list any minerals or pseudo-minerals in this case as primary species here. So we have calcite and CO2 gas. Next, we list out all of the secondary species. And again, remember to check that all of the species names are consistent with what's written in the database. Okay, and then finally, we add names and labels of reactions that have those TST rate laws. And so we have calcite and CO2 gas here, where both reaction labels were named default. All right, next we have the initial condition, or CINI file. And here there are 3 blocks, one for precipitation, one for the shallow or upper zone denoted by UZ, and one for the deeper or lower zone denoted by LZ. And so under each heading, we list out the primary species in the same order, along with their initial concentrations, which are approximated here with the average concentration for each species in precipitation chemistry for the precipitation block, shallow soil water chemistry for the UZ block, and deeper groundwater chemistry for the LZ block. And then concentrations for mineral species are actually volume fractions. Now, since we don't have measurements for the volume fractions of calcite and CO2 gas, we've approximated these values based on our understanding that calcite minerals are generally more abundant in the deep zone compared to the shallow zone, as the calcite in bedrock is less weathered in the deep zone. Similarly, we know that CO2 gas is typically more abundant in the deep zone compared to the shallow zone, partly because it's easier for CO2 gas to escape to the atmosphere from the shallow zone. And then species that have associated reactions, so calcite and CO2 gas here, also have several parameters that need to be listed, including their specific surface area or SSA, kinetic rate constant or log K, which should match what is in the kinetics block of the database. These species also have Q10 values for the dependence on temperature, soil moisture threshold value and exponent value for the soil moisture dependence, and the N-alpha value for the depth dependence function. All of the values in this file can be tuned during the calibration process. All right, and lastly, we have the precipitation chemistry files, which are just the time series of precipitation chemistry for all of our primary species. And note here that any species without a significant concentration in precipitation can be given a value of 10 to the minus 10 for all time steps, but we should avoid using the value of 0 anywhere, as this will cause issues with model convergence. Also note that the dates in the precipitation chemistry and numerical experiment precipitation chemistry files should match the corresponding dates in the HBV results and numerical experiment results files. Great, and so that's it for the input files, but to quickly summarize, the files that need to be amended when setting up a carbonate weathering reaction in BioRT include the chem file, where we list out all of our primary and secondary species, as well as the name and label for mineral reactions. We then have the initial condition file, where we specify the initial concentrations for aqueous primary species, the volume fractions, specific surface areas for all of our mineral or solid species, and any dependency factors. And then lastly, we have the precipitation chemistry files, where we have time series of precipitation chemistry for all of our primary species. Right, and so that's it for this video. Thanks very much for watching. And in the next video, we'll cover running BioRT in a Linux system, the output files of the model, and we'll look at some simulation results. Thanks.